Welcome to this session of Shadow the Scientist, Observing the Sun with the Daniel K. Inouye Solar Telescope. My name is Jamika Marshall, and I am pleased to serve as the Shadow the Scientist Coordinator. Shadow the Scientist is an initiative housed under the Creating Equity in STEAM umbrella of programs offered by a team at the University of California, Santa Cruz. The National Science Foundation's Daniel K. Inouye Solar Telescope, or DKIST, is a 4-meter solar telescope on the island of Maui, Hawaii. It's currently the largest solar telescope in the world. Now, with a focus on understanding the sun's explosive behavior, observations of magnetic fields are at the forefront of this innovative telescope. The Inouye Solar Telescope reveals features 3 times smaller than anything we can see on the sun today, and does so multiple times a second. Observing the specific fingerprints of hundreds of atoms and ions throughout the solar surface and atmosphere will help us explain the dynamic nature of the sun's behavior. Now, in this session, you will learn how professional physicists and astronomers assess weather conditions to determine which science objectives to target. Once the objective is identified, the scientists will zoom in on the sun to find the features to help unlock the mysteries hidden within its magnetic field. This magnetism is responsible for space weather events like sunspots and solar flares. To get us started, let's head over to Sarah, who is going to be our guide, one of our guides for this shadow session today. Sarah, aloha, and thank you for allowing us to shadow you and your colleagues today.
Aloha, good morning. I'm Sarah Yeagley. I'm an astronomer at the Daniel K. Inouye Solar Telescope. That's a facility funded by the National Science Foundation, and it's a national and international facility for observing the sun. We're also going to have Evan Pasquale joining us, and he's going to be our eyes in the sky, viewing and zooming in on various activities that we're up to here at the telescope today.
Excellent. It's thrilling to have you both as our guide on this journey. And yes, Evan, if you're there, please feel free to introduce yourself and kind of get us oriented in where we are, because I am actually in the DKIST office here on Maui. I'm super excited to be here, and you're going to kind of orient us before we get back over to Sarah to jump into the science.
Hi, everyone. Thanks for having us today. As Jamika and Sarah mentioned, my name is Evan. I'm here with the National Solar Observatory. I am the communications specialist on our education public outreach team. So a little bit about my role is I take all the exciting science that people like Sarah and the other astronomers are doing here at the Inouye, and I'm taking that complex science and helping spread the word and share it with the world. Science is for everyone. We engage with our local communities, global communities, and it's a really fun job. I deal with a lot of media, creative media, photography, video. Maybe one day I'll be a influencer, so to speak, on social media for the Inouye. So we try to get these fun, amazing stories out, the amazing science, technology, and people that work here at the Inouye. We have several support facilities. One of which is our Science Support Center, which is about an hour below the summit. So the crew comes up here in vans. It's about an hour drive up a windy road through the national park to the summit of Haleakala. A fun fact is Haleakala means house of the sun. So it's pretty cool that as the world's most powerful solar telescope, we get to operate from the summit here. So today, because we are on the sun, safety is paramount. There's a lot of energized parts of the facility that for safety reasons, I can't necessarily take us into while we're on the sun, but what I can do is kind of show you a walkthrough of what the crew does when they arrive here on the summit. So I'm gonna flip the camera around This is the entry to the Inouye. It's a bit windy outside, so for audio purposes, I'm going to just give you a look through the window here. This is one of our support buildings, our utility building. Another fun fact, because we observe the sun, it's very important that we keep all of our instruments cool and keep the mirrors cool, the optics. That way we get the best possible data when we observe the sun. And this facility here in the center is our utility building that deals with a lot of the coolant. It produces ice at night, and we have about 7 miles of pipes that run through the Inouye to keep the facility cool. So when the crew arrives, here's the entry. There's a sign-in sheet. And we have a couple ways to navigate the facility, one of which is the elevator. That is probably the preferred method because here at 10,000 feet in elevation, air tends to be a bit thinner. But today I'm going to take the scenic route and go up the stairs with you all. There's several levels to the facility, and the level that I'm taking you to now, oops, turning around here, is what we call the mez level. This is where a lot of our office spaces are, where people hop on for meetings for the day. We have conference rooms. And so here, I can give you a quick look. We'll turn this around again. So this is what we call the mez level. This is the second floor of the Inouye. Here are some of our office space, some of our team at work. The image you see in the background on the wall there is one of the early photos that the Inouye produced of a sunspot. We have a lot of monitors here to keep eyes on the facility. This particular screen tells us which parts of the Inouye are energized. And here on this screen, we also have a lot of different views from inside the Inouye, so we can safely observe what's going on at the telescope level with the instrument lab. So you can see here a bit better image of what's going on today. And of course, we have some exterior monitors to be able to monitor the weather conditions at the Inouye. So the next stop that I'm going to take us to is the third floor, where the control room is. And in the control room is where we have the drivers of the telescope, the operators, the scientists, the duty engineers. It's where all of the action takes place in terms of pointing the sun at, or the telescope at the sun and getting all of our instruments aligned. So here, I'll turn this around again. Oops. We're at what's known as the coude level. The coude level being the heart of the telescope where all of our scientists, science instruments are. Give you a quick look in here. This is known as our computer room. So it might be a bit loud, but here's where, let's see if I got the right. Oh, 1 second. Okay, the other door. Here we go. This is our server room, where a lot of the computers are stored to process data. Keep the Inouye running. So we have a software team here that works on that. And then here's a general pan of the control room. This is where our other host, Sarah, is tuning in from. Some of our scientists are currently working here. These are all the different monitors that our team uses when observing the sun. Now, behind that shuttered windows where the coude lab is, where the instruments are actively studying the sun. This gives you a really good idea of all the monitors and different screens and tools that the team here uses. And there's another look at the other side of the control room. So from that, I think I'm ready to hand it over to Sarah here. Thank you.
All right, thanks, Evan, for that really good overview. Today, I'm sort of sitting in the back seat in terms of observing. I'm not actually running the observations myself today. There's another crew, scientists and telescope operators are science support, actually running observations on the telescope. And it can get hectic. So in order to do this broadcast today, I think it helps to have me sitting back here and not being involved with the observations directly, so I can focus on talking to all of you. But they are trying to get set up on a sunspot right now to do some solar observations. And also running calibrations. I'm gonna let them continue to try and sort that out. We do have some thin clouds today, so the conditions are a little suboptimal for actually running science observations. But all of the time on the telescope is precious. So even when we aren't doing scientific observations, we very often run tests of the instruments, tests using sunlight or calibration lamps, and also other tasks for the observatory that can only be done when it's actually ready to operate. When we go into an engineering mode, we take everything offline. We don't have sunlight coming into the facility, so things can be accessed safely. But it doesn't, in that state, often doesn't give you the chance to test things fully. So having sunlight in the facility is important.
Sarah, you mentioned that there were some high cirrus clouds that could potentially impact observing today. Is there a public cloud cam link that you could share with us, or that we could maybe see some of the a view out right now?
Sure, I can go over some of the tools that I typically use when we're running observations. We keep very close eye on the weather, both locally and across the Pacific, because we watch the weather patterns coming in, and look to the future on how those might affect us. So I will share my screen here. This one. So I just have a couple of links. This is actually a view of the sun today. This isn't from DKIST. This is from the Solar Dynamics Observatory, which is in space, but it's one of the tools we use to see what's going on the sun and pick out targets. But let's go look at what the clouds look like today. So this is a infrared satellite image, and it's enhanced to show actually dust. It's in, a couple of different infrared channels that are processed to show dust. And so the very light pink are low-level clouds that are traveling just above the surface of the ocean. And then they come and wrap around the island and usually don't make it up to the summit where we are here on Maui. But you see this band of dark black, red, and purple coming across from the southwest. And that's the high level cirrus that we're currently in. We're actually sort of in a hole in the cirrus, but you can see that there's stuff coming in behind it, so it's likely to continue throughout the day. So that may impact the observations that happen later. Of course, we look at the detailed weather forecast for the summit. It's not always accurate, so it's always better to look outside. And this is actually from our neighbors. The Institute for Astronomy at the University of Hawaii is next door, and they have two telescopes called Pan-STARRS, and those are synoptic telescopes. They take nighttime maps of the sky every couple of nights. So they're constantly looking for new things, looking for asteroids, but they have a nice all sky camera that we can look at, and it operates both at night and during the daytime. and I can sort of scan through. You can see sunrise as it happens, and you can actually see in this time lapse the cirrus clouds passing through pretty widespread. And the two telescopes you see here on the north side of this camera and on the south side are the Pan-STARRS telescopes, but DKIST is right behind it. So sometimes you can actually see our dome rotating. Actually, you see it there. It rotated as they were starting to get set up for observations earlier this morning. So it's just peeking out just barely on the south side there. And as Evan showed us, we also have many views throughout the facility. And we have cameras pointing outside in each direction so we can see the clouds coming in. Sometimes we get clouds that build up on the crater and start to rise up to the telescope level. So we always try and keep a good eye on those. And it's not so evident in this sort of fisheye view from the camera on Pan-STARRS. In addition to the weather, we pay attention to what's going on the sun. Like I said, this image here is from the Solar Dynamics Observatory. So this is a current image of the sun. So these sunspots are basically what you would see right now. The wavelength I've got here is actually in the ultraviolet. It's not something we would be able to see from the ground. DKIST operates at wavelengths in the visible and infrared. So that's what gets transmitted down through the Earth's atmosphere. We can't see the ultraviolet because the atmosphere blocks it out. But we can see the very extreme blue, violet, and near ultraviolet, and then out into the infrared. And that's where our instruments primarily operate throughout the visible and infrared wavelengths. But the Solar Dynamics Observatory gives us the view of things that are occurring in the ultraviolet and extreme ultraviolet. We can see in an image like this one, oh, maybe that opened in a different window. An image like this one, we can actually see the sun's corona. And the Daniel K. Inouye Solar Telescope is made to look both at features on the solar disk, that's this area of the sun, and up above in the corona, in that very thin outer atmosphere, which we see really only clearly during a total solar eclipse. But the Inouye has special baffles and field stops to block out the light from the main disk of the sun so that it works as a coronagraph, so that it can very sensitively measure what's going on in the sun's outer corona. And it's 1,000,000 times fainter than the disk of the sun. In the extreme ultraviolet, like you see here, the corona is actually pretty bright as compared to the solar disk, and you see all kinds of features and loops. These are the loops that we're trying to see with DKIST out when we do observations above the solar limb, so above this boundary, we see the edge of the sun. But we're looking at the sun in the visible wavelengths, and the disk of the sun is actually quite bright. So this is a visible wavelength image from the Solar Dynamics Observatory, and this is basically what our eyes would see when you look up at the sun through a telescope with a solar filter. So we see a bunch of sunspots. And this is typical for the phase of the solar activity cycle that we're in right now. The sun goes through an 11-year cycle of solar activity from one magnetic polarity to the other, and then back is the full cycle is 22 years, but from sort of a minimum in activity to a peak and then back down to a minimum is 11 years. And we're at the peak of that cycle right now. And when the magnetic activity is at its peak, we see a lot of sunspots. Sunspots are caused by the sun's magnetic field. That's where the magnetic field and the loops of magnetic field are poking out vertically through the surface. And the normal pattern of convection that you see, this sort of speckle pattern in the background, the convection is suppressed. So that in a sunspot, because there's less convection, there's less energy transport into it, it cools down. So it actually gets darker and redder. We can't really tell with our eyes that it gets redder, but it does. And the sunspot also has a penumbra. That's this sort of filamentary feature that we see surrounding it. In the middle is the umbra. So the magnetic field is super strong and vertical in the sunspot umbra, and in the penumbra, it's actually turning over to be more horizontal as you get further out from the very strong vertical field. Yeah, so
this is so dynamic, and I mean, I can hear everyone behind me talking, because this is I'm on the mezzanine level that Evan showed us earlier, and it's just, I can feel the energy. It's so exciting. And even though this is from the Solar Dynamics Observatory, I know that, similar conversations about things are happening here too. And it's incredible. These views are so special of our local star. Looking up at the sky, we see all these twinkles of light, these points of light, and to now be able to have a better understanding of our sun and what it's doing, but to know that that's also happening on all these other stars is incredible, because we call these sunspots, but they're star spots, right, Sarah?
That's right. Yeah. Our sun is a star, and these are spots that on a distant star, we may not actually notice them because they're actually a small fraction of the total area. Although with some of the new observatories in space, they're actually pretty cool. So they can detect sunspots on solar-like stars. Some other kinds of stars have even more extreme activity. Actually, stars a little bit smaller than the sun have much stronger convection, and they can actually produce really huge sunspots. It's thought that some stars actually have a sunspot at the magnetic pole, just covering the entire pole, which is kind of crazy to think about. But one of the things that drew me to solar physics was how dynamic it is, and it's definitely on a human time scale. So we see sunspots. So this is just right now. But the sunspots actually, the sun is rotating, so the sunspots rotate around. So we can see them rotating, but they actually evolve in that time that they're facing towards us on the front side of the sun from our perspective. So maybe I can load up one of these movies. I think this one has a video, a 48-hour video. Let's see if it goes.
Wow.
So you can still see the sunspots here, but you can actually see the bright regions around them. And these are strongly magnetic regions surrounding the sunspots. You also see all these bright flashes, and that's flare activity. So these are probably small flares occurring in these various regions as the magnetic field is evolving. It does something called reconnection. So the magnetic field is generally continuous and it forms loops, but sometimes those loops get stressed and they snap and reconnect with each other to form a different configuration. And at that point, there's a huge release of energy. It's the biggest explosion in the solar system. our solar flares. So yeah, and this is just 48 hours. So we see these sunspots not only rotating around the sun, but these regions are evolving. And if we looked, can I zoom in? I don't know. If we look at them in more detail, you can actually see them moving. There's features that are flowing out from them. And there's just all kinds of activity going on. And then there's the speckle pattern in the background. This isn't noise. This is actually real solar signal. The granulation pattern is sort of ringing up and down. There's this whole field, which I am not an expert in, called helioseismology, which studies how the sun is ringing like a bell. And you can actually use helioseismology to do things like detect sunspots on the backside of the sun that we can't see. You can actually look at the vibrations and tell that there's a big magnetic concentration on the backside. So sometimes we get warnings from our friends over even within the National Solar Observatory. They say, oh, we predict this new large sunspot that's coming around the backside. You better be looking for it. So it's a really cool field of study, which I don't know enough about.
Well, Sarah, this is incredible, incredible. To see this video is just knowing that it's just 48 hours of activity, and to see it so up close and live, essentially, for us, to see the reconnection happening is it's a dynamic experience. I'm so glad that you and Evan are our guides here as we explore it some more. Now we have lots of questions in the chat, so if we can go to that, I will start with, let's see, our first question was from Vani, and Vani asks, does global warming affect what your scientists see when observing the sun?
It definitely affects our weather here. That's what I would say. I mean, it affects the Earth's atmospheric conditions. So, when we built or when we chose the site for the facility, something like 20 years ago, the Earth's atmosphere was different. The climate was different. So things are changing, and we don't quite know what to expect as we move forward, what the future observing conditions will be like.
I see. And so I imagine that you all have had to be very dynamic and flexible in being able to adapt to those kinds of changes.
Yeah, certainly. I mean, the mountain weather keeps us on our toes. So we can have extreme wind. It can snow up here, even though we're in the tropics. We are at 10,000 feet. So during the winter, January, February, we typically get a little bit of snow. Sometimes we get an ice storm. Sometimes the storm can bring down the power lines, and we're stuck without power for a week or so. So yeah, the weather can be extreme up here. Typically it's beautiful, but it can be extreme.
Oh, that I can imagine. It was certainly something driving up this morning. It's beautiful, certainly beautiful, but I got to experience a lot of that wind you were just talking about. So another question from Vani. I'm just going down the line here. And again, everyone, please post your comments and questions in the chat throughout the session, and we will definitely get to them. So another question from Vani: is your vantage point, or I guess I would say your location here, beneficial for observing the sun? Is this better than other locations, and why? So clearly this site was chosen for a reason. Could you maybe give us a few of the main reasons why this is an optimal location?
Yeah, Haleakala is really special place, both environmentally, culturally, and in terms of its climate. So we're on the island of Maui, and Hawaii, the island chain, is isolated in the middle of the Pacific. We're thousands of miles from the nearest continent. Um, so that means it's a very low dust site. And the fact that we're at high altitude here also means that we're above the majority of the water vapor in the Earth's atmosphere. But Haleakala is probably a better site even than Mauna Kea for observing the sun. And the reason for that is the very deep blue sky. We have very low dust here. Over on Mauna Kea, it's a bigger mountain and it's broader. So I mean, I can see it over there out the window. But it's a bigger mountain and it's broader. So you get wind that can sweep up to the summit, picking up dust as it goes, to make the near observatory environment sort of dusty during the day. And Haleakala is a little bit steeper. The summit is pretty small. So we have I would say much darker blue skies than even Mauna Kea.
That's surprising. So another question from Vonnie: how is the sun different from other stars in the universe? And I think you've already touched on this. You said that smaller stars tend to have more sunspots, maybe at the pole. So our sun is a G2V type star. So smaller stars would be maybe the K and M type stars.
Yeah, that's right. I mean, let's see. I'm an astronomer, so I should know the answer to this question. The sun is really typical. It might be slightly above average in terms of the size of typical stars in the galaxy. But it's actually quite low activity with respect to some other stars that are the same mass as the sun. And that's actually pretty good news for us, because that it means it's actually making pretty small flares. Large stellar flares could be devastating to the Earth, where we are in the orbit. So it's good that the sun is boring, but of course there's larger stars than the sun. When you get to higher mass, larger stars, the sort of internal energy processes and the structure starts to change. So in the sun, we have a fairly thin outer convection zone. And then inside, the core is radiative, and the core is burning hydrogen into helium through the proton-proton chain. And that's typical for stars around the sun size and smaller. As you get through to smaller and smaller stars, they have an even thicker convection zone. And the convection zone can reach down into the hydrogen burning region. And when that happens, things get pretty crazy. The stars get really mixed. And for stars larger than the sun, the convection zone shrinks until you get to like blue giants. So those have a radiative envelope.
Yeah.
And I think convective core. But the energy source for those is actually different. They're not doing hydrogen burning, or they may do hydrogen burning as a minor part of their energy source, but they do primarily the CNO cycle, carbon, nitrogen, oxygen. So they're fusing atoms up to iron. So they continue to add neutrons to and perform atomic reactions until you get up to atoms as heavy as iron. But the sun doesn't do that.
So our sun
we're,
does
we're
not do-
just we're just doing hydrogen and helium, and that's basically it.
I like it. So these are great questions, you all. Keep them coming. So Johnny asked, what technique is used to acquire the solar image? Lucky imaging or speckle imaging or something else?
Yeah, maybe we can look at some of the images that they're taking with the telescope right now. Maybe I can switch over to one of the computers over there. So I will stop sharing here. And move over to the computer here. Let's see, and I'll share. Share only. I guess I have to share the screen. Okay, that's fine. Okay. So now this is what we're looking at right now with DKIST. We're currently pointed at the middle of the sunspot. And let me sort of fit this image a little bit better to the screen. Ooh. The scale. Let me try manually. There we go. A little bit better. Oh, too much. Oh, there we go.
Yeah.
So this is what we're looking at right now. And this is one of the cameras. The view from one of the cameras. I don't know that we're actually running anything right now, are you? No, not actually running anything right now.
Clouds hang out great.
Yeah, the clouds are not cooperating. So the seeing is a little wobbly, so that means that atmospheric conditions are not very stable. So they're making things a little blurry when we look at them.
Yeah.
But this is what we're pointed at right now. So it's a sunspot.
Yeah.
And this is one camera. So this is the visible broadband imager, and it has a couple of different channels to pick from. And this is actually hydrogen alpha. So this is the most common spectral line probably in the universe. Hydrogen alpha. So it's hydrogen emitting at a red wavelength. And we're looking at the sun with that. And the sun actually looks pretty cool in hydrogen alpha. Get it a little bit better here.
You also move a little to the left to get
Yeah.
this few filaments.
Oh, yeah. So there's all of this. I mean, there's the sunspot umbra here, but there's all of this filamentary structure that you can see. And this is actually part of what's called the chromosphere. So the sun's outer atmosphere sort of has layers, and the deepest layer that we see is the photosphere. So that's where we see basically all the sunspots and granulation. And when you move outward, the next layer up is the chromosphere. It's actually a little bit warmer than the photosphere, and maybe we'll talk about why that is in a few minutes. And then we go out into the corona. So we have basically those three layers, the photosphere, chromosphere, and corona. And so the chromosphere is actually material which is up above the sunspots, up above the surface, and it's quite three-dimensional. So you can see that there's these fingers of what's probably cool gas, shown by hydrogen alpha, that's funneling into the sunspot, probably into the edge of the sunspot penumbra or into the umbra. And the sunspot umbra itself is not just, you know, a monolithic dark thing. It has all of these features and speckles, which you can sometimes see a little bit better or worse, depending on what the atmosphere is doing. And then there's this really bright thing. I think that's related to activity going on in this sunspot active region. So this instrument in particular, the one that's doing the imaging, the visible broadband imager, it does it's capable of doing image reconstruction on the fly. Or should be capable of doing image reconstruction on the fly. A lot of that image processing is currently going on by hand because we're still developing the techniques. But in the future, it should be able to do that on its own as we collect the data. So we take in a whole bunch of images, and we could do lucky imaging, which is selecting out just those images with the highest contrast. So that's an option. Or we can do a full reconstruction of the image using the point spread function of the telescope. So we take a whole set of images and process them together using special techniques to pull out what the sun actually looked like, because with the series of images, you have many different realizations of what the scene you're looking at looks like with different seeing conditions as the atmosphere is moving. So you can sort of normalize all of those image motions out to get out what is actually the highest quality image. And the best images from DKIST have been processed that way. So the first light images that you see have been processed to pull out those really fine details. So I was talking about the Solar Dynamics Observatory before, and that takes a whole image of the sun. You see the whole sun, but it's not particularly high resolution. And the Inouye Solar Telescope is like a microscope. So we're zooming in on just the small region of the sun to get at the details in that region. And it's actually hard for the Inouye to look at the full sun or map the full sun because it's so large with respect to our field of view. And it looks like we're moving off to something else right now. Little blurry there.
Yeah.
Yeah. So I can change the view that we're looking at. Maybe you can see. Try this again. So you can see this is in the visible blue light. So now we're just looking at the sunspot and penumbra and the surrounding granulation pattern from convection. Still a little blurry. And it may get better or worse as time goes by.
This image allows us to segue perfectly to the next question. This is from Roger. Roger asks, Does immediate current solar activity provide any forecast of likely aurorae in the short term, like 12-hour short-term future around that time scale?
Yeah, absolutely. It can take a few days for activity on the sun to reach the earth, but the energetic particles actually travel really fast, and they can come interact with our magnetic field and uh and satellites and stuff. They're actually quite fast, so it's almost immediate, traveling near the speed of light.
Another question from Vani, and you all, these are fabulous questions. Keep them coming. What is at the center of the sun? Or is it just homogeneous? But I think you've already spoken to that. It's not. There are definitely layers, right?
Yeah, there's layers, but at the core of the sun, it is kind of homogeneous. It's very dense and hot. The hydrogen burning is happening, actually not. I mean, the core burns, it actually gets depleted of hydrogen. So but yeah, the core of the sun is basically this soup of energy. I mean, you have hydrogen and helium, but super dense. And as the fusion process is going on, there's high energy gamma rays emitted. The energy that comes from fusing hydrogen and helium is actually a gamma ray. So that's scattering all around in the core of the sun. And those gamma rays try to travel outward through the surface, and it takes them a really long time because they keep bouncing and scattering off of other atoms, and by the time they finally get out to the surface, they get absorbed, and then by convection, the convection brings it up to the photosphere, and then it emits in mostly the visible and infrared. So that's how the energy gets out from the inside of the sun.
A question from Laura Mae Abram, who is one of our previous Shadow the Scientist hosts. She joined us in our first session from the NASA Infrared Telescope facility on Mauna Kea. So, so glad you could join us, Laura Mae. And so the question is, what would be causing large sunspots on the poles of these other stars that you mentioned, Sarah?
The stars have a magnetic field, and like our sun, they have a mainly dipolar magnetic field. So it comes out of the North Pole and then goes back in on the South Pole, like a dipole magnet, like a bar magnet. You've got the magnetic field coming out, and then it forms a loop, and then it goes back in the other side. So on a star where that dipolar magnetic field is really, really strong, we think that that the field pointing directly out of the star suppresses the convection there, and that's what makes that polar sunspot. It's just like sunspots on our sun, only we have different, it's like little horseshoe magnets sticking up in various places, and then you get loops where the sunspots are forming at their base. But on this, you only have one magnetic field loop, and it comes out of the pole and goes back in the other pole. And so, yeah, along that rotation axis, you get sunspots on each side. It's not something that has been observed. These are on really small stars, and so they're very difficult to see. But sometimes we see things with really strong magnetic fields, and weird thermal signatures. So it's thought that something like that is possible.
And that leads well to our next question from Annalise, who is another one of our frequent participants and working on her PhD in astronomy and is a member of the Astronomical Society of South Africa. And then there are several members of with her joining us today. So thank you all for being here. So the question is, are there any recent scientific findings published from the observations that have been taking place here at DKIST?
Mm-hmm. Yeah, and I actually have a couple of examples which I can talk about a little bit. I did want to point out what's currently going on the screen. So the observing crew is pointed over at the edge of the sun, and what we're actually looking at now is again hydrogen alpha, and this is actually cool material which is suspended really far up above the sun. And so the edge of the sun in this image is actually here. And then this huge sort of flame-like structure that we see is a filament or prominence when it's called when it's on the edge there. So this is cool material that's suspended in a magnetic field up above the surface. And it's one of the major magnetic features that the sun can produce. Sunspots are one of those. And then filaments are another kind. So this is actually pretty dense material, pretty cold, but it's just held up by the magnetic field. And it's a little blurry here because our adaptive optics system does not currently work on the edge of the sun, but we're actually working on a low light version of adaptive optics, and that can be used especially for filaments. And it's actually being tried out at the Goody Solar Telescope at Big Bear Lake in California. So we're already working towards something like that. It's going to be pretty cool.
And so if you'd like to maybe show us some of anything related to some of your discoveries, that would be fantastic.
Sure. I will stop sharing here for the moment and move back over here. So I actually pulled up some papers which you might find useful or interesting. I'm primarily someone that is interested in instruments, although I do solar science sort of end to end. I like to know about telescopes and the instruments that go on them so that I can use them and then understand how they impact the observations that we can do on the sun. And I have to know also a lot about the solar science that's going on. But there's a collection of articles specifically for the Daniel K. Inouye Solar Telescope. So that's this. It's part of the journal Solar Physics, and it's open access, so you can go in and look at any of these articles. So there's various articles here. Maybe I'll scroll down to the bottom. The very first one is about the observatory itself, a whole overview of the observatory. There's one about planning science, the science that this facility was designed to do, and what different interesting investigations would be useful. And this is really community-driven investigation. So a bunch of different authors got together and put all of their ideas into this paper. And then there's papers for each one of the instrument systems. So there's one for the visible broadband imager, which is the images we were just looking at. All of the other instruments on DKIST are spectrographs or spectropolarimeters, and quite complicated and interesting. So there are various other papers here for each of them. So there's one for the visible spectropolarimeter, that's VISP. The diffraction limited near infrared spectropolarimeter, DLNRS, but that's actually the instrument that I'm an instrument scientist for. And so you see my name on that paper. I wrote that one. And also the cryogenic near infrared spectropolarimeter. It's a close friend of DLNRS. They're right next to each other on the observing floor. And that's by Andre Feldman. He's actually our observer up here today. So he's the cryo-NERSP instrument scientist. And very important to the telescope, there's this paper on polarization. How do we calibrate polarization for the telescope? The polarization is extremely important for how we measure the sun's magnetic field. So there's very many optics, and how those optics change the polarization in the telescope is really important to how you calibrate your observations. And so there's this collection of articles, which I'd invite you to go look at. So again, that's in the journal Solar Physics, and it's a collection for the telescope here. I also pulled open what I think is probably the most one of the most important papers that we've published so far. And this is by Tom Shad, another scientist here on Maui. And he's working with Andre and the rest of the team, working on the cryogenic near infrared spectropolarimeter, cryo-NERSP, to look at highly ionized silicon that appears in the solar corona. And this line, a spectral line, it's an emission line in the corona, and it's really only been observed a few times ever. So one of the motivations behind cryo-NERSP is observing this line, among others. There's more out there. So this is at 1430 nanometers. So that's in the infrared, but it's fairly close in the infrared. So our eyes cut off at about 700 nanometers, maybe 650, 700 nanometers. And then this is out at 1430 nanometers. So definitely not something our eyes could see, but and it's actually quite faint in the solar corona. So there's a lot that goes into this. The silicon 10 line actually appears like this. So it's this tiny little blip in the midst of all of this absorption from water vapor. So it's this tiny little window that we can see in the midst of the spectrum of water vapor, which is all in the Earth's atmosphere, or most of it. The silicon 10 is just this tiny blip. So we're trying to interpret that signal in the midst of all of this noise. And I believe there's some actual maps of what it looks like. So I mean it's sort of a blurry blob, but this is actually the solar corona, and you can actually see the coronal loops pointing out here from the this region. So the center of the sun is down off the bottom of this image, and we're looking upward from the solar disk. So out here is further from the sun, and down here is closer to the sun. So Tom has done the analysis for this line and measured its Doppler velocity and its width, and amplitude to provide us with the first real maps of this this extremely ionized silicon line that's out in the infrared.
I'm definitely going to check out that paper, and I'm sure others will too. I did drop that Springer link to that collection of DKIST papers in the chat also for everyone.
Yeah. And this one is also in the Astrophysical Journal. So it's open access currently now too.
Open
It
access.
says open access. Yep. Right up
Yes,
there.
so grateful for that. Okay, so Richard asked, sorry, let me go back here. Is there some way of looking at layers deeper than the chromosphere, like using like what ground penetrating radar can do on Earth?
Yeah. So from the chromosphere, we have the photosphere, which is basically what our eyes see. That's basically the deepest layer that we can see. Depending on the wavelength, we can actually get a little bit deeper into the photosphere at one wavelength than another. It turns out that the minimum, like the lowest that we can see is actually in the infrared, and it's one of the wavelengths that we use with DKIST. So that provides us with the deepest that we can see from the light emitted from the surface. But that's a boundary that we cannot see through. So we can't get photons from beneath that layer to know what's going on. But like I said, helioseismology is studying the sun ringing like a bell. So that technique can actually, looking at the oscillations of the sun, we can actually tell what's going on in the inside. So there's still some uncertainty with using that technique, what we're actually seeing. But we think we can see down through the layers of the sun, which are very rapidly rotating through in the convection zone. So there's the sun is rotating, but it looks like the inside actually rotates faster in some regions than the surface does. And it rotates at different speeds depending on what the latitude is. So there's a lot of velocity structure inside of the sun, and helioseismology is the main tool for trying to figure out what is going on there.
I see. And I think that answers Richard's next question.
It's kind of, well, is it like radar? It's more like using earthquakes or vibration to figure out what the structure of the earth is. Because you see, you can measure earthquakes or the shaking from earthquakes and from different places on the globe, and try and figure out what's the density of certain material of rock, or what the core is made of, depending on how the vibrations are bouncing around. Very similar technique.
Mike asks, will our sun change its size over time? And I guess yes, once it's off the main sequence.
Well, it's changing right now, but very, very slowly. So there's sort of this paradox. It's called the faint young sun paradox, in which the sun, when it first started hydrogen burning and came onto the stellar main sequence, it was actually smaller radius. And as time goes on, there's mass that's added to the core, even though the sun is actually losing some mass. It's blowing stuff out through the solar wind. That's actually a small fraction. But the core is growing in size, and that actually pushes the outer layers out. So the sun's radius is actually growing, and its luminosity is increasing. But in the past, it was smaller and less bright. So the paradox refers to what was going on the Earth at that time. Given that the sunlight was less, how could life actually evolve? How could it be warm enough for life to develop on Earth if the sun was fainter at that time? But this is the evolution over millions of years. When we look at how the sun is changing, even on the 100,000 year time scales, is very constant in its intensity. But as we get to the end of its lifetime, another 3.5 billion years, it will be a little bit bigger and a little bit brighter until it totally runs out of hydrogen and things start to get interesting.
Things will definitely get interesting then. I had not heard of that faint young sun paradox. To find out more about that. Let's continue with these amazing questions. Viren asks, why is the solar cycle every 11 years? Is this timeline for the cycle changing? And what's happening in between these 11-year cycles?
Yeah. So the solar cycle has been more or less 11 years for a long time. The exact beginning and end of the solar cycles is sometimes difficult to determine. There's not a sharp boundary. So sometimes it might be 12 years long and others 10. But over recorded history of sunspot cycles and in the geologic record of Earth, we can look at ice cores and tree rings and figure out sort of what the solar activity cycle was. It's really been fairly constant in terms of this 11-year cycle. What causes that? I think it has to do with just the rotation velocity of the sun and the mass that it is. I think looking at other stars similar to the sun, you see a variation in how long their cycles are. It might depend on how old they are. I'm sort of reaching, I'm not quite an expert, but I know a little bit. And I have colleagues that work on this kind of topic.
We next come to another question from Laura May. So what do you make of this cycle being more energetic than the original NOAA predictions, which were that there was going to be a fairly calm cycle 24? And does this happen often with predictions of an upcoming cycle?
It seems like the predictions of solar cycles is either you're right or you're wrong. Or is it going to be a stronger cycle? Is it going to be a weaker cycle? Or is it going to be the same? And people publish predictions, and we don't know enough to really know what the next solar cycle will be like. I think the current solar cycle is a little bit more active than the previous one, which was actually quite low. But I don't put a lot of stock into solar cycle predictions. It's entertaining to look at them before the solar cycle happens and then see how people update them later. But it's definitely an active area of research. How does the sun's magnetic field get generated? And how does the dynamo in the sun get wound up, because the sun's magnetic field is ultimately produced by the circulation of charges inside the sun from plasma. So as we've got rotating plasma, that's a current, and currents make magnetic fields. So people are trying to model what is going on the inside of the sun, even though we don't know very much. And we can only get small details from what we can see on the surface, and then what we can glean from what's going on the inside from helioseismology. We're trying to put all of this information together to figure it out, but it's still very much an open question of how all of these processes work in detail.
As you're talking about magnetic fields and how this is an open area of research, very recently we've been having these X-class flares from the sun, and it creates beautiful aurorae just in general, but they've come further down into places that have never seen them before. Yes, and so could you speak a little bit about aurora in general for those who may not understand, well, like myself, exactly how they're generated because of the interactions with particles with our magnetic fields, and then the kinds of other space weather that DKIST, along with other facilities, help to monitor.
Yeah, so solar flares and coronal mass ejections are two kinds of activity. So solar flares, and both can cause aurora. So solar flares, primarily we get the radiation from the sun. So we see the sun flash bright, it produces a ton of ultraviolet radiation that comes, it can ionize the Earth's atmosphere a little bit more. That very outer layer, because all of that ultraviolet gets absorbed in the outer layer. It can make it a little bit puffier. And then we can also get coronal mass ejections, which is actually material and magnetic field that gets expelled from the sun and travels out through the solar system. And especially when we get magnetic field from the sun coming to interact with the Earth. The Earth has its own magnetic field. And so how those fields can interact is important. Sometimes a coronal mass ejection can come past the Earth and it doesn't do anything. But sometimes it has the right polarity where it interacts with the Earth's magnetic field and causes a cascade of particles that travel along the magnetic field lines of the Earth. So those particles can then come and impact the regions around the poles, because that's where the magnetic field of the Earth comes back in toward the ground. And so very often you see the aurora at the North and South poles because of that. But if you have a large enough event, enough particles that are traveling around in populating this magnetic field around the Earth, then you can start to see all of this aurora everywhere else, basically. I mean, the one I think that happened in May, you could also see from Maui, not naked eye, but you could see it with a camera. It was pretty spectacular. I didn't see it because it was cloudy. But I think my parents saw it in Portland, and people all over the US saw it. So that was fantastic.
I was out to hopefully see it on Big Island, but it was not only cloudy, but it was raining. So I missed it, but I did enjoy the pictures from everyone, and it certainly got me extra excited about this first session with you all. And so as we are heading into our last 13 minutes here, could you maybe tell us a bit about what's happening now in the control room and the status of observing?
Yeah, could we take a walk around with you guys to see all the stuff that you're working on? Yeah, if you want to use the camera. So we'll switch over to Evan here.
So yeah, I'm David. I'm one of the operators here at DKIST. So this is our operator console where we control the telescope. On the right-hand side here, we kind of keep our instruments. So all their instrument interfaces, we do that work. And over here is, I was kind of pointing around to different targets for you guys a little bit ago. So this is what I was using to point around. It's basically a point-click interface, so you can click wherever you want on the solar surface and point there. This is where we also run our experiments for all the scientists. So they'll submit what experiment they want to do. I don't know if Sarah went over this with you. But they'll submit whatever science goals they want. The scientists decide if it's a worthy experiment, then create an experiment for it, and then we run it for them. So that entails kind of taking the instruments and deciding what instrument wants to run for each experiment. Also from this console, we monitor weather. So as we've said, the clouds are inhibiting us a little bit today, but I'm glad you can still see a bit of the solar surface. And yeah, I'm monitoring health here as well, all the systems, there's a lot of things to keep track of. Yeah, this is where it all happens.
Yeah, we can talk to Anthony.
I'm one of the operators as well. Today we're not having the best conditions for having corrections, but as we go back and forth, Tuesday we do see a difference. But typically the atmosphere is too wiggly, too turbulent, and too unpredictable for the wavefront to see the breadth of the capacity. Don't worry. I got it.
Anything else you want to show them? Maybe we could show, we haven't also really looked at this, have we?
Oh.
Yeah, so I don't know if you guys saw it all. I'll try to get this up here, but here are some of the different views of the DKIST. So you have different cameras. And top right, you can see the telescope room with the M1 mirror. The top left, you can actually see parts of the Inouye lab. The optical, the lights passing through the different instruments. This gives everyone a good view of what's happening inside the telescope.
I'm changing this now. So minutes in the filter there.
That's what those flash of lights were. So after we see this,
We can look at the data. So this is a view of what the observer would be looking at while the observations are being taken. So it shows a view from every instrument that's currently collecting data. So the image in the upper left that shows the whole sun is actually our sort of external reference. It's a little telescope on the side of DKIST that's running at H alpha. So that telescope's looking at the whole sun, gives us the context for what's going on around the tiny field of view that we're looking at. And then you can see the 3 images below it are from the imagers. So we have one from the wavefront correction system, and then 2 from the 2 different cameras on the visible broadband imager. And so those are the images that we were looking at a little bit before when we were looking at a sunspot with H alpha and in the continuum. The images just to the right of that actually look a bit funny. So we put in a calibration target, and that's the pattern that you're seeing now superimposed on the sun. And they're just getting set up for some calibrations. Yeah, rotating.
Show this so you guys can actually see movement of the Kude line. That's in the center image there, image off to the left of that.
Yeah, could we talk about the spectrographs? So, the visible spectropolarimeter, and cryoners and DLNers, those are the instruments I mentioned before. Those are all spectropolarimeters. So it's a spectrograph with a polarimeter on it, but primarily a spectrograph. So the images that we see in the right-hand side of this image, in the center, and then over here on the right, are from the visible spectropolarimeter and the diffraction emitted near infrared spectropolarimeter. And those take a slice through the image. That's what the VISP is doing here. So we're sampling through that image over on the left-hand side, just one slice through it. And then we're just dispersing it out by its wavelengths, and looking at very specific channels of the spectrograph. In this case, I think this is calcium 2 in the very extreme blue, and there's the sodium doublet, which is a really common astrophysical line to look at. These lines both give us magnetic field information, thermal information about the sun. I think the bottom channel isn't anything specific, may not have the filters in it right now. And then, so this takes a slice through this solar image and then disperses it outward. And DL-NIRSP actually is what's called an integral field unit. So it actually takes all of the light from a tiny little postage stamp on the sun, and it slices and dices it into different spectra that that get dispersed through the instrument. So it looks quite complicated. And that's why it looks like a stack of bricks or something like that. Its view is a little funny. But it's quite a new style of instrument that we're still figuring out a little bit.
It's great to see inside the control room and see live what's happening. This has been an incredible session.
Yeah, thank you so much. And I hope everyone was able to enjoy this view of what we do on a normal day here up at the telescope. Thanks so much for joining, everyone.